Okay, for this proof by induction, we are proving that this mathematical statement, this expression here, is divisible by 9. So we have to think about a few things. What does it mean to be divisible by 9? What does this statement right here mean to be a natural number? And what are the 3 steps of mathematical induction that we repeat in every single proof by induction? So I'll start with those 3 steps, steps of induction. Okay, so the first very informally is we're going to show that the statement is true for the first case. What does the first case mean? Whatever your very first number possible that you can use. And for the natural numbers, I'll go over what those are in a second. Second step is assume statement is true up to a new number different from n, and usually denoted by a new letter we use k. Okay, that won't involve any math. We're just going to make an assumption there. And then the last step, usually the most computation heavy one, which will be to prove next after making the assumption in part 2 that the statement will then be true for the subsequent case. So that'll be the k plus first case. Okay, so there's the 3 steps. Definitely could have written it more formally, but this is in a nutshell. Now let me go over as promised. What does this part here mean? N in the set of natural numbers, right? So that means N is part of, inside of, an element of this bold or capital N is the natural numbers. And that just means positive integers or positive whole numbers. So that means N can be, whoops, N can be any of the following, starting with the first positive integer, which is 1, 2, 3, to infinity. All the infinitely many positive integers. So it doesn't include 0, fractions, decimals, only whole numbers, and only positive ones. So that's why for this case, we say it's typically n equals 1. I say typically because sometimes the problem tells you to start with maybe like the number 2, for instance, or maybe it's not even natural numbers. And can include 0. But for this case, we're starting with or using just natural numbers. All right, now we're ready to start with the actual problem itself. Okay, so step 1 shows the statement is true for the first case, which means I need to figure out what happens when I plug 1 into that expression. So I'll do that down here, step 1. N equals 1, and putting that into 4 to the n plus 15n. That was multiplied, not to exponent, minus 1. So what does that look like? Now replace all your n's with the number 1. Use another color. That exponent changes. This product is times 1 now. And so I get 4 plus 15 minus 1, which, if my math is correct, that's 19 minus 1, 18, right? And what on earth did we even do that for? What are we trying to show? We're showing the statement is true for the first case. What was our statement? That whatever we put into this expression will always be divisible by 9. And lucky for us, I think 18 is divisible by 9. That's a multiple of 9. So great. Step 1 is done of induction. Step 2. Now we're just no math involved. Just we're going to make an assumption that will really help inform step 3. So we're going to assume that the statement is true when you go back up here, up to a new number k. So again, k is some value different from n, typically also less than the value of n, where n can represent any natural number, and k is a specific unknown natural number, but that's where we're going to assume the statement is true up to. So up to that value. 4 to the k plus 15. I should have this memorized by now from writing it down so much. So that is divisible by 9. For all values up to that new magical number k. Right? So that could be, let's say k was the number 10, for example. So this statement or expression should be divisible by 9 for all numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 up to 10, just for example. But we're leaving k as unknown, some value less than n. And I was going to say I did mention earlier there's no math involved for this step. It's just an assumption that informs the next step. But I think what would be really helpful is to just kind of notice what does it mean to be divisible by 9? And like we had here, it just meant that your value is a multiple of 9, right? So it could be 9 times anything, 9 times 1, 2, 10, 12, right? So to be divisible by 9 means 4 to the k plus 15k minus 1 is a multiple of 9. Right? So that's what this means. And I can even make that an even shorter sentence with just mathematical symbols and say that 4 to the k plus 15k minus 1 is equal to 9 times a new value, which we've already used k, we used n, so why don't we say a? Okay, so that's what we got from this inductive step here. Okay, so that will help us later. Step 3. Let's go back and see what was step 3 of induction. Prove the statement is also true for k plus 1, and then we'll be done. So k plus 1 is now going to replace the k's here and here. What will that look like? Now we have 4 to the k plus 1 plus 15 times k. Oop. And then minus 1. And what do we want to show for this? We just need to show this is also divisible by 9. Divisibly by 9. Okay, so that means at the end we should get through some steps and ultimately have all that equal 9 times some new value. Okay, it could be a letter, it could be a number, but as long as we can factor out a 9 out of there somehow, some way, then we'll know we're done with our proof. All right, so I want to manipulate this expression a bit, see what I can move around and doctor up. So, well, I know that I could kind of use product rule in reverse, which when I split this up, right? And that's the same as 4 to the k times 4 to the 1, right? Same base. You can add up the exponents. Oh, made a mistake. So if you were wondering, is she going to correct that? Yes, the moment came. Way, way later. Yes, that was supposed to be a k plus 1. You were correct if that's what you were thinking. And so now I can do some distribution. Get a 15k plus 15. And minus 1 didn't have any k's next to it, so it just stays the way it is. Okay. What else could we do? I think the only thing we really can do is combine this like term here, and everything else is immovable, unchangeable. And does it look like we get anything divisible by 9? I don't think so. But I'm going to take a look back at my inductive step up here, step 2, and try to see if there's any like overlap connection I can make with that final step or line that we got to in step 3. And there are some similarities. Like I see a 4 to the k here, 4 to the k there, but this kind of messes things up because that's doesn't match up with the inductive step 2. There's a 15k. There's a -1. That was there. It just got, right, embedded into the 14 or turned into 14. I think the best thing we can do here, rather than trying to force the last line into the inductive step, I think if I go in reverse and try to somehow change this state expression and fit it in here, that will give us something, hopefully, fingers crossed, divisible by 9. So how can I go back and work on this line here? Well, you can solve for some things. Like I notice 4 to the k is usually the it's an exponent. It's hardest to sort of break apart past that. And so what I'm thinking is to leave that by itself and move everything else to the other side. So what would that look like? I'll make some space over here to show you. Just rewrite it again. Okay. So let's move that 1 over. I get 4 to the k plus 15k equals 9a plus 1. This will make some kind of sense after we isolate. For now, it just looks like we're moving things for no reason, but there is a method to the madness. So now the 15k is on the other side, and 4 to the k is on its own. It's equal to 9a plus 1 minus 15k. Okay. And again, these exponents typically, it's hard to work with, aside from that product rule I did in reverse. But these non-exponential expressions and terms, you can work with and move around more and more likely to find like terms in that way. So that essentially was my way of trying to eliminate any exponents in that last line here that you'll see, because now what I can do, now that I have this line, again, this was the same as my inductive step here. These are the same statements, just moved around, right? But now what I can do is wherever I see, I'll highlight it for you here, a 4 to the k, I can now make a substitution, and I do see a 4 to the k there. And that's wonderful. Now we won't have any exponents to deal with. So that 4 to the k, I want to replace it with all of this. I now have 9a plus 1. That a, again, was just a placeholder for being a multiple of 9, which can be any number. But let's make sure we're consistent. So again, the highlighted parts are all the same and replaced. But all of this, I want to not change or substitute anything, so that we're going to keep integrity of that. Plus, that was a weird plus sign, plus 15k plus 14. Okay, this I can work with, I think, a bit better. Me personally, I prefer to work with numbers like this. We don't need that power to the 1, do we? 4 to the 1 is 4. Okay, so I see some distribution I can do here. For example, 4 times 9a, 4 times 1, 4 times 15k. And we're going to end up with 36a plus 4 minus, what's 15 times 4? Goodness gracious, 60. Okay, so that's all distributed out, and just keep the rest of the team here. Wonderful. Like I said, now this looks like something we can more manage and combine like terms, right? Like I see a like term here and here, and these are also like terms. So what do we get all together? 36a is all by itself, doesn't have anything to combine with, but 14 plus 4, ooh, this is looking great. It looks like a perfect multiple of 9. Negative 60 plus 15. I hope that's a multiple of 9. I believe it is. Why is that so important? What did we say at the beginning? We just need to factor out a 9 out of all of this somehow. And lucky for us, all of these can factor a 9 out of them. Plus 2 minus 5k. And how do we know we're done? Remember, the first statement we were trying to prove is just to show that no matter what you plug in, we plugged in the first number, 1, then we made an assumption that is true for up to a value k, and after we plugged in the next value after k plus 1, we still get a value that is a multiple of 9, and that's what it means to be divisible by 9. So we have proved step 3, which was the k plus first case. I don't know, how do you make it to enumerate that? K plus first case. That we have a multiple of 9 at the end. Therefore, we can now safely assume by way or by proof of induction that it's true for all natural numbers n. 4 to the n plus 15n minus 1 is always divisible by 9. Because again, there was a generality there. I don't know, what you guys use, QED or the box to show that you're done. But yay, we're done. Again, that's the importance of k being very general. It could be any number. And so if it's true for some value we picked k, then and as well as any value after that, then you can replace k with any natural number, and should always be true for that as well as the number after that, and infinity and beyond. So that's how we do a proof by induction for this problem, following the 3 steps of induction.